All right, so we are still on electricity. I think I need one more class to finish up this topic. So on Tuesday also we'll talk about electricity. Then on Thursday we'll move on to magnetism. All right, so by now we know about static electricity a lot, I guess. So by rubbing different materials together, we can separate the charges, right? Basically, we are moving electrons here and there and make materials either positive or negatively charged. And there are two types of charges, which is positive and negative charges. And Benjamin Franklin named those charges. And then there are actually there are three types of materials that we'll talk about these materials in the next class, but roughly there are main two types of materials divided into categories depending on the electricity conductivity. So there are conductors and insulators. In between we have semiconductors that we developed for our purposes. So basically there are three types of materials: conductors, insulators, and semiconductors. All right, there are main two type of charge transfer processes, which is conduction and induction, and polarization comes in between these two, making things polarized, like separating charges to the two sides of the object and make one side positively charged and the other side negatively charged. So polarization is something in between conduction and induction, but you are using polarization to make things charged by conduction and things charged by induction. So we learned all of these in the previous class. All right, so we know that if we bring a positive charge closer to another positive charge, it repelled. Similarly, if we bring a negative charge closer to a negative charge, they repel, right? Like in the demonstration I did on that video. So in the Van de Graaff accelerator, everything gets positively charged. So when we have something attached to that, all those pieces get positively charged. And later on, as they have equal charges, I mean equal sign of charges, they all are positively charged in that example. So they get repelled. So equal charges repel. But if we have unlike charges, they will attract each other, right? So we know that. But how can we explain it scientifically? Why does positive charges repel and why positive and negative get attracted? Have you ever thought about it? We don't care, right? But there's a good scientific definition or explanation for that. Okay, so if you think about a positively charged particle, so in electricity, we can separate these negative charges and positive charges. It's different from magnetic things. In magnets, we cannot separate North Pole and South Pole, they're together. But in electricity, it's easy to have a single charge particle. So we can have positive charge and negative charge separated. So if you think about a positive charge, sorry, excuse me, it has electric field around it. So in a positive charge, electric field always spreads out. So these black color lines represent the electric field lines. In nature, we can't see this, but it is there. Okay, so around a positive charge, the electric field lines goes away from the positive charge, it spreads out. It's like sunlight, right? So it spreads out. It's emitting the electric field lines outward direction. So positive point charge always radiate the electric field lines equally in all direction, and it's away from the positive charge. Okay, so if you put it into a good scientific wordings, we would say for a positive source charge, the lines will radiate outward. So we call this as a source because that's the particle we have. So that source is a positive charge, so it's emit the electric field lines in the outward direction in radial directions. Radial means, like if you think about a ball, I don't have a ball here. So if you have a ball, let's say this is a ball. So radial means like if you go for the center and if you travel a bit out toward the surface, like in this one, so you're going from the positive sign in the center and you're going towards the surface of the circle and going outward. So this is called the radial direction. So in the radial direction, For a positive charge, there are electric field lines that spreads outward, like in this picture. Okay, so a charged particle with charge Q. So let's say there's a charge amount of Q there, and it is producing an electric field in the region of space around it. So we call this as a source charge. Now, let's say I want to test this out. So I am bringing a test charge, which is, let's say, Q naught. This is just for symbol, like Q naught. That to represent the test charge. So I'm going to place a test charge somewhere in this field. So I'm going to place it somewhere here. Okay, so it is here. So I bring a positive test charge there, and the charge amount is Q naught. And then what is the electric field that feel by this guy due to the source charge? So due to the source charge, like there's something like, let's say, wind coming towards you, and you are the test charge. So you feel that wind coming towards you, right? So similarly, this test charge will feel that electric field comes towards that. So now if we separate the test charge and the source charge, this is what you see. So there will be an electric field. This symbol represents the electric field. So there's an electric field that acts on the charge, the test charge, that's going outward, starting from the positive charge. So here's the direction of electric field. Now let's isolate this and go a little bit in detail here. So for a positive source charge, here it's the same picture. So here's the positive source charge, and this is the test charge, and there's an electric field. Now, this is another theory. So when we have a charged particle in an electric field, then it will experience a force. Force means push or a pull, right? So this test charge will experience a push force from this electric field. Now, you know, like in physical world, if you want to push something, then we need to press on it, right? So there's a physical contact there. But in electricity, there's no physical contact, but due to this electric field, there will be a force acting on the test charge. So we call these as non-contact forces. So there's a non-contact electric force that's act on the positive charge. So it acts this way. So the equation is force equal the test charge times the electric field. We didn't talk about Newton's law yet, but in the Newton's second law, it says force equal mass times acceleration. So this charge, whatever the force that's experienced by the test charge, is equal to the acceleration. And acceleration can be calculated using this equation. Now, you might get confused with all these equations. Don't worry, I'll give you the equations if you have to do a calculation. So this is just for explanation purposes. So this is the theory. That's the force directions come from. So force is in the direction of electric field. So this positive charge will experience a force in the direction of electric field. So you see, like this test charge will experience a push from the positive charge here. It will experience this way. So that will create a push. So they repel. So this positive charge and this positive charge will get repelled. So basically that's due to the electric field that created by the positive charge. So they get repelled from each other. Now, if we have a negative test charge here, so negative test charge is here, and the electric field goes that way. Now the negative, right? So the charge is negative, so there's a negative sign here. So it will reverse the direction of force. So this test charge, which is a negative test charge, it will attract towards the positive charge. Now these pictures might look new to you, but all these represent the forces. So this line here, the orange color one, that's represent the electric field. So that's why it's labeled as E. This blue color dash line represent the force. So you see, like the force acts towards the positive. How do I know it's towards? So see this arrow direction, it's going towards the positive charge, right? So this positive charge, negative test charge will receive a force that's towards the positive charge. So it's get attract towards the positive charge. So that's why they get attract to each other. All right. So when we see, like when we keep positive, they repel, like in this first example. Then if we bring a positive and a negative charge, they attract because of this electric force. Electric force is a non-contact force. Okay, now take a minute and on a piece of paper, think about what is the electric field look like for a negative charge. Now I mentioned for a positive charge, electric field spreads out, radially outward. Now if we have a negative charge, what would be the direction of electric field? Now if we place a positive test charge within that electric field, what would happen? Now it is a positive test, negative source charge and a positive test charge. So they should attract, right? So the electric field of a negative source will be towards it. Then when you keep a positive charge, there will be an electric field acting on the positive charge radially outward, but force will be in the opposite direction, so they will attract. All right, so I'll share another screen with you, and I'll show you using a simulator. No, I have to stop share, and I have to share a new screen. Here's my. Hold on, it's not available for me to share. Okay, so here we go. Share screen. Oh, please wait. Let me find this screen. It's not available here. Sorry about the wait. Here we go. Okay. All right. So do you see a simulator?
Yes.
Okay, nice. All right. So let's say I drag a. Hold on. What is this? Put me back. Okay, nice. All right, so you see, now here in this simulation, these are called PET simulation. It's PHET simulations, and it's free source, and you can use it at any time if you need. But I know you don't need it now. But if you're taking the lab class, we might use this in the future. All right, so here what I'm going to do is I'm going to drag a positive charge here. All right, look at that. You see these white color arrows that represent the electric field. So when you have a positive charge, it produces electric field lines that spreads out. Okay, so I'll put this back and I'll bring a negative charge. Look at that. For a negative charge, the electric field lines it's coming towards the charge. All right. Now, if I keep a test charge here somewhere, look at the field direction. So this red color arrow represents the electric field that filled by this charge. So this charge experiences a electric field that's coming towards the negative particle. All right. Now let's combine two particles. So I have another positive charge and a negative charge. You see these electric field lines? They never cross each other. See, like it's create a field lines, but they are not crossing. Electric field lines never cross. So they create a nice pattern that electric field lines start from the positive charge and going towards the negative charge. Now what happens if I bring a positive charge here? Okay, I'll remove the negative charge. So I have positive here. All right, now look at this, the pattern. So the electric field lines start from this positive charge and it's try to go away from it, but there's another positive charge that stops it. So they are bending away. So the field lines goes like upward. See, it starts from here, but it goes there, upward. They're not merging towards each other. And the field lines never cross each other. So you see the overall effect is it's going from positive, but it goes away. Start from positive, it goes away. But if I have a negative charge instead of a positive charge here, look at the field lines. It starts from positive and goes towards negative. So it always travels from a positive charge towards a negative charge. to a negative charge. All right, so stop share screen. I need to go back to this PowerPoint slide. Okay, so this is a picture for electric field lines for each particle. So for positive charge, electric field line spreads apart away from in the radial direction. For a negative charge, it's always coming inward in the radial direction. Okay, so this is the summary about the electric field lines for each particle. For positive and negative, their directions are different. So electric fields have its own directions depending on positive or negative of the charge source. Okay, from the question that I asked you, like if you have a negative source charge, remember like I had list of questions that you have to think about and draw it on a paper. So if you have a negative charge here and you are bringing a positive test charge, then the electric field lines at the positive test charge is coming towards the negative charge. So this is the electric field direction. And if you apply the equation, then the force is going towards the negative charge. So the force acts this way. So that's why negative, positive attract. And also, as there are force acting on it, like if you push something, it should move, right? So if you push it, it should accelerate. So this particle will get accelerate towards the negative charge, so they get stick together at the end. Now here, if we bring a negative test charge here, so electric field lines goes this way, but the force will be in the opposite direction because they are repelling each other, right? So force will be this direction, then the particle will get accelerate that way. So they repel from each other, traveling away from each other. So negative, negative or positive, positive will stay away from each other. But unlike charges like positive, negative, they attract due to this reason. All right, so now let's look at an application of this idea. So, you know, like we are using microwaves every day, most of the time, right? So how do we heat up the food using the microwave? So, you know, like in any food, we have water molecules in there. Water is H2O, that's the chemical symbol. So this is H2O, right? So we have 2 hydrogen atoms and 1 oxygen atom. So basically, if you draw the structure of water, it looks like this. So 2 hydrogen atoms here and oxygen over here. Maybe you have learned about water in schools or in your chemistry class, right? So here the oxygen, here's the hydrogen and hydrogen. So hydrogen has a partial charge of positive when they are combining with oxygen. So basically on oxygen, there are 2 valence electrons that's combined with the valence electron on the hydrogen. So they're creating a bond here, keeping 2 hydrogen with angle with the oxygen. So basically the shape of the water molecule is this. It comes with an angle like this. This angle is about 104 degrees. Okay, so this delta negative and delta positive represent the charge of the atom. So this oxygen is negatively charged, twice negatively charged, and hydrogen is positively charged. But they attract to each other from these forces. There's a high bond between these two, right? So basically, as you see, the oxygen is charged negatively and hydrogen charged positively. So those are charges, right? So we call this as a dipole. So we have positive charge on this side, on the bottom, and on the top, on this picture, it is negatively charged. So we call this as a dipole. It is not separated, positive and negative, but they're combined and stay a little away from each other. You can watch this video. It's a water molecule motion.
This short video is going to show you a little bit about those intermolecular bonds that you see between water. So it's a slightly different just now to this. So I noticed that here we have 2 hydrogen gas molecules. One hydrogen gas in Paris, that's our green, and one of the blue ones are the oxygen gas molecules that are down to one.
All right, so in this one, I'm not sure whether everybody can see it, but it is on the PowerPoint slide that you can watch if you want. So this blue color represents the oxygen and the green color represents the hydrogen. This is real microscopic view of water.
Samantha, we can't really hear in the video.
Okay, that's enough for us. It's mostly kind of a chemistry in there. So you notice like hydrogen and oxygen separate their charges. So positives on one side and negatives on one side, but they are bonding together by hydrogen bond and a covalent bond. But they are in a chain, so that we can separate positive and negative into two sides. So we call these as a dipole electric fields. Sorry, dipole. So there are, if we keep this dipole in an electric field, then it will experience a force. Now here, let's say this is the oxygen molecule. So, oh my God, I'm making mistakes. So no, let's say this is the high water molecule. So we have one is negatively charged and the other side is positively charged, right? So this is a dipole. So we have positive and negative separated, but they are not physically separated. They are just distributed in that way. So now if we apply an electric field in this direction, let's say I'm applying an electric field in this direction and here's a positive charge. So this side should experience a force in there. There should be a pull or push coming from the electric field, right? So there will be a force acting on that side, on the positive side of the water molecule. Similarly, there should be a force acting on the negative side, which is going in this direction. Now, if you have something like this, and if you pull it from this side towards this way from one side, and in the other side, you're pulling it in the other way, so it will try to rotate, right? If there are two forces acting on a lever like this, like from this side, you're pulling it this way, and from this side, you're pulling it this way. So the center part will try to rotate around, right? So this molecule will start rotating due to the electric field. But the net force, the total force acting on the molecule is zero, because this positive force and a negative force, they adds up to zero, but this get rotated. So we call this as a torque. So there's a torque acting on the dipole molecule here. Right? Now, when it's come to the parallel condition like this, there are no forces acting on it, so it's balanced, so it's stopped. But due to the momentum, it will rotate a little bit and then it will come back. So it will keep rotating within the electric field. Okay, so in summary, like if you think about this way, so there's a force acting on the top and another force acting on the bottom. So we call this as line of action. So it will rotate around the center point. So basically, this is a water molecule. So we have hydrogen over here and oxygen over here. So they get to rotate around. So there's a torque on the dipole. So don't read this whole thing, but I'll take you to a simulator and then we'll come back. All right. So do you see a simulator with a thermometer and a molecule here?
Yes.
All right, nice. Okay, now this is a simulator of a microwave. So I'm going to switch on the microwave. So you will see like what happened to this molecule. So basically this is a single water molecule, but in real water, it is not isolated. There are so many molecules that combine together. So now let's switch on the microwave. Microwave means you are sending a electric field as a wave. So this green color line represents the wave. Do you see what happened to the water molecule? It starts rotating, right? So due to that electric field, this water molecule will start rotating. Okay. Now, why it is heating up then? So let's look at the chain. So here's a water molecule in a chain. Again, in the water, it is not in a chain. It's like combined in the whole container, right? But let's look at the chain here. So microwave on. All right. Now, each molecule get rotated and they are going to bump to each other. Now, as you're rubbing your hand, it gets heats up, right? So that's basically the molecules rub against each other or bump onto each other. So here, as you notice, this thermometer, the temperature rises because of this collisions. So it heats up due to the collisions. Now let's add many molecules. So this is the real condition. So there are so many water molecules inside water, so they get bumped to each other and heats up. So let's switch to microwave. See, like whole thing get oscillated, right? So each molecule get bumped into each other and heats up. See the rising of the temperature? So you can, using a microwave, you can heat up the water really quickly because of this bump to each other. Okay, so is it safe to heat the water inside a plastic cup in microwave? What happened to the molecules in the plastic? That's also get vibrated, right? Depending on their polarity. So there might be an effect. So in scientific research shows like we should not microwave anything in plastics. Glass is fine because glass molecules are not that much movable. But always don't use a plastic cup to microwave your food. There will be some effects that's coming from that. All right, so let's look at a coffee. Inside the coffee mug, so you're heating up. So let's start sending a microwave. So see, like microwaves pass through the ceramic. If you use plastic, it goes through plastic, and then it vibrates the water molecules in there. Coffee is mixed in there, but water gets vibrated first, so it gets heats up. Okay, so basically that's happened due to the electric field and the forces that's created by the electric field depending on the charges that we have. Okay. It's almost 10:15, so we only have 30 more minutes to go. All right, so I'll take you to top hat again, and then we'll take attendance, and then we'll do a couple of questions there, and then we'll continue on the lecture. For some reason today I have a hard time sharing the screen. It's not filtering it correctly.
So cute.
Yeah, if you don't have questions, please mute yourself. Always you can disturb me if you want to stop me and continue on. All right. So let's take the attendance. Not that one. I need to go to the other one. Nope, cancel. Oh, no. Sorry. Please stop it. I need to take attendance. All right, so please send your attendance code. Yeah, I noticed about 5 students doesn't have top hat access yet. So if it is due to a financial issue, let me know. So these grades will be uploaded to Canvas gradebook by this weekend. So if you didn't have access to top hat, then I will look at your participation on the Zoom, and then you will get credit for this week. But starting from next week, I'm counting only the participation on top hat. So we are slowly going towards using top hat. It's easy for all of us. So things are available on one place. Okay. Okay, let's do a question. Okay, so I'll stop counting the attendance. Right, so this is the first question that we are doing for the participation credit today. Oh, we already did another assignment. Okay, okay, so here in this picture, we have a electric field lines drawn. And if you cannot see it, you can always maximize the picture by using this icon here. Okay, so it's asking the field lines due to two spheres with like charges are shown by, so likely charges like positive, positive or negative, negative. So what is the correct picture that shows the correct direction of electric field lines for likely charges? So it should be positive, positive. So in each picture we see positive, positive, but what is the correct pattern of electric field lines? Okay, let's look at your answer. Yeah, so almost all of you got correctly. So yes. So for those who didn't answer it correctly, you have to look at, first you look at the symbols on the charges. So you see like it's positive, positive. The color coding make us a little bit confused because it's colored positive, red and blue. It really doesn't matter. That's our color coding. So we can use any color to label these. Usually in textbooks, we use red color for positive and blue color for negative. But in this picture, even though we are using different colors, we label this as positive, positive. So we see like those are likely charges. Then likely charges repel each other. So the electric field lines cannot be connected. So the answer should be B. Now, if you look at this one, it's starting from positive and going towards the positive. It is impossible. Always electric field line starts from positive and go towards the negative. So when as in this picture, it started from positive and it cannot go towards this because this is another positive charge. So it's go away from that towards searching for a negative charge. So somewhere here, there should be a negative charge. We don't know. But positive charges behave like this. It's trying to navigate the electric field lines going away from the positive charge. Now this picture is correct if we have a positive and a negative charge. So this should be positive and this should be negative. So positive charge is emitting the electric field lines and the negative charge is collecting it towards it. Okay, so you will see a very similar question like this in the exam and also on the homework. So it might not be identical to this, but very similar. So I might ask, like, if you have two different types of particles, what would happen? Okay, so stop share. Oh, can you give us more time to answer top part questions? Yes, sure, next time. Okay, so, and present one more question. Do you see a question open up from your account or not? I can't.
No.
No.
But then it disappeared when I clicked on it.
Yeah, same.
I think I have to show it on my screen, otherwise it won't pop up on your side. Okay. This is a little tricky question. You might easily get trapped. So it's asking the direction of electric field lines shows the, what does it show? Do you need more time? Okay. Okay, let's look at it. Okay, so I like the first answer better than the other, but I would take answer D as well, because you see like size of the field. Oh, hold on. The question. So read the question, the direction of electric field lines. So it's asking about the direction of the electric field lines. So it's very specific here. It's asking the direction of electric field lines. It's not about electric field lines, but it is specifically about the direction of the electric field line. Yes, so size of the field, it can't be, because size is depend on the length of the arrow. Okay, the strength of the field, no, it's not represented by the direction. Direction is only showing the direction of the force on a test positive charge. Right, this is the catchy word, the direction of the electric field lines. If it is only electric field lines, I would take size of the field, strength of the field, because it depends on the size of the arrow and the pointy of the arrow. So yeah, answer should be A. I'm sorry, most of you got it incorrect. But this is the catchy word here, the direction of the electric field. Okay, stop share. My computer is out of battery. Give me a second. Let's move on. Let's spend about 10 more minutes on move on to the next topic. I mean, electricity, but continuation of it. Okay, this is the part 3 of electricity. Let's look at an equation, a little bit in detail. Okay, so we learn about electric field directions and how to represent that on a picture. Now, the electric force and the electric field and the charge amount will connect each other. Okay, so that's given by this equation, which is E equal F over Q. You might think, oh my God, that's just letters, right? No, it's not letters. Those letters represent something. That's a very important quantities. All right, so this E represents the electric field strength, and then F represents the force acts on the charge, and Q represents the charge of the test charge. Okay. All right. Now we're going to do simple calculations using this equation. So if you are given with the force and the charge amount, then you should be able to calculate the electric field. Can you do that? Now let's say you have given the force and you given with the Q, the charge amount. So basically you need to divide the force by charge to calculate the electric field. right? So I expect you to do that simple calculation. So on the homework, you will see these questions to do some small calculations. All right, so well, this force, that is a force, right? So the force are measured in newtons. The units to measure force is Newton. Like when you are measuring something, like let's say you want to measure the distances. So we use miles, right? So in scientific units, we are using, SI units, we are using meters. So likewise, to measure the force means push or a pull, we can measure these forces using the unit Newton. So, the scientist Newton, right? So it's coming from his name. So force measured in Newton, and the charge, the units of charge is Coulomb, lowercase c, okay? Newton, uppercase N. It's fixed. You cannot use lowercase n to represent Newton. It's uppercase N. Likewise, Coulomb is lowercase c. All right, now let's look at this equation. So the electric field is force divided by a charge. Now force is measured in Newton and charge is measured in Coulomb. So you get Newton divided by Coulomb. So the units for electric field is Newton per Coulomb. Okay, now you will ask, like, do I have to remember this equation? No, I will give you this equation in the exams or homeworks. Even though I forget to give it in homework, I will give it in the exams for sure, right? So only thing you need to do is you need to know what are these symbols represent. So I'll give you this equation, E equal F over Q. Then you need to know F represents force, which is in newtons, and Q represents the test charge that measured in Coulomb, and E is the electric field. Now I know the unit for force is Newton and charge is measured in Coulomb. So the units for electric field is Newton per Coulomb. Right? So it's like unit price, like if you buy 10 apples for $20, then price per one apple, price per apple is $2, right? So likewise here, charge, force per charge. Okay, so electric field is a vector. That means it does have a direction in there. There's a scalar, that means the amount, and there's a direction involved with the electric field. All right, so Maxwell, the scientist Maxwell, is the major contributor to the electric field concept. So there are Maxwell equations that we use in upper level physics classes to do all these calculations. We don't use those in this class, but remember, like, there are Maxwell equations that we can use to do electric field calculations or electric related calculations. Then Faraday also developed the idea of field lines. So it is like field lines means there should be a visualization to the electric field, right? So Faraday is the one who visualized these electric field lines, and he proposed that there's a direction and a strength involved in this field that we learned earlier. So there are a bunch of properties that's involved with electric field lines. We already learned that, but let's summarize it. So field lines must begin on a positive charge and terminate on a negative charge, or at infinity in the hypothetical case of isolated charge. So if it starts from positive charge and there's nothing around it, then it will go all the way to the infinity. Then the number of field lines leaving a positive charge or entering a negative charge is proportional to the magnitude of the charge. It's depend on the size or the amount of charge in the charge that's create the field lines. So if we have a 1 Coulomb charge and a 100 Coulomb charge, then definitely the 100 Coulomb charge produce more field lines than the 1 Coulomb charge. Then the strength of the field lines is proportional to the close census of the field lines. More precisely, it is proportional to the number of lines per unit area perpendicular to the lines. Okay, that's make us crazy, right? So that means Like if you have a positive charge, honestly, I don't have any demonstration materials at home. So let's say this is the positive charge, it's a tiny one. So it's emitted electric field line. So if you want to calculate the field that comes into one area, you need to find a square type region, area, and calculate the field in there. Okay, so that's one concept, but we are not going to do big calculations using this step 3. Okay, then the last one, the direction of the electric field is tangent to the field line at any point in space. Tangent means it's perpendicular to the surface. So if you are looking at electric field lines that acts over here, always electric field lines comes perpendicular to this surface. All right, so here are a couple of pictures that shows the field lines. We call this as the superposition of electric field lines. So we did a practice question on this. So if we have positive charge and a positive charge, then electric field lines superposition to create a field like this. So you see, like in the center, there's no field, right? So we are using this concept to navigate charges. So we can send a charge particle through this area. So that's something we are using in the accelerator experiments. See, like there's an empty space with no electric field, right? So that's very interesting. Then if we have a positive and a negative charge, then the electric field line superimposed in this pattern. Okay, so higher strength in this area. Then if you have a negative charge and a negative charge, then the field lines to come towards the negative charge. So this is the pattern. It's very identical to this pattern, but look at the direction of arrows. So this one, arrows are starting from positive and going away, but for negative, it comes towards. All right, so for the exams and homework, you need to remember these shapes. Okay, you will be tested on this. Okay, so now you know, like positive charges and positive charges repel due to the electric field that's created from the source charge on the other one. Then the other one act like a source and create a field lines on the other charges. Then they repel or attract depending on the field directions. There are so many things over there. All right. Okay, so I'm not going to move forward doing any calculations. I feel like it is a little bit heavy lecture today. So I'll stop from here. If you have any questions, you may stay here. But before you leave, I need to tell you one more thing about